In the fifth part of my lecture on sampling, I'm going to be looking at an example of applying measurement errors to the isotope calibrator. The isotope calibrator is used for measuring activity of radioactive sources in nuclear medicine, and so it's important to know that every measurement is accurate, and also important to know how precise measurements are. That's why the calibrator is subject to a regular QC program. And we're going to look at how statistics can be applied to this. The precision of the calibrator is due to the repeatability of the instrument. We'd expect the variation over a large number of readings of the same source, that is, the population of lots of measurements. The standard deviation of that population gives us the repeatability of the instrument. But in practical circumstances we have to estimate that from the variation of a small number of measurements when we put in a check source, so we just have a small sample. So we take the sample standard deviation and apply the Bessel's correction in order to estimate the population standard deviation and take that as a measure of the repeatability. If we just take a single measurement, then we take the precision of that as the instrument precision that we can determine from some repeat measurements of a check source. If we are able to take an average of several measurements, then we can determine the precision by the standard error of the mean. But of course the accuracy of the measurement can only be determined by comparison with the standard instrument. But all of these things are important to the use of the isotope calibrator. So we're going to look at some data obtained as part of the QC program of an isotope calibrator, where we've got 10 repeat measurements with a cesium-137 check source. Here we're doing a quality control check of the isotope calibrator that's used for checking patient doses. We put a standard check source into the calibrator to see what it reads. This is a source of cesium-137, which is used because it has a long half-life and doesn't decay very much between readings. And we see 7.66 megabecquerels is the first reading. We then take the source out again and put it back to get a repeat reading. We have to wait a little while for the reading to settle down, but when it does we have a second reading of 7.67 megabecquerels. We take the source out and put it back in again. And the third reading is 7.66 megabecquerels. We're going to do 10 readings altogether so that we can get a good measure of the mean and the standard error of the mean. The fourth reading is 7.75 megabecquerels. And the fifth reading 7.75 megabecquerels. The sixth reading is 7.70 megabecquerels. This is a routine calibration measurement that should be done regularly on all calibrators to check their precision. The seventh reading is 7.74 megabecquerels. The eighth reading is 7.78 megabecquerels. The ninth reading is 7.65 megabecquerels. So doing it this way, not only will we get a good measure of the average reading, but we'll also get a good idea of the variability from one reading to another. And the final reading is 7.65 megabecquerels. So we saw there that the 10 readings that we obtained were 7.66, 7.67, 7.66, 7.75, 7.75, 7.70, 7.74, 7.78, 7.65 and 7.65 megabecquerels. So the questions that we would like to pose are, first of all, what is the percentage precision of the calibrator? Secondly, what is the best estimate of the activity of the source? Third, what is the 95% confidence interval for the activity of the source? Fourthly, what is the percentage precision of the activity measurement as opposed to the precision of the calibrator? And 5, when the source is measured in a standard instrument, it's found to have a true activity of 8.05 megabecquerels. So what is the percentage accuracy of the calibrator? And finally, if a syringe of Technetium 99M gives a calibrator reading of 73.2 megabecquerels, what is the best estimate of the activity in the syringe? So here are our isotope calibrator readings. Those are the 10 readings that we saw, and they sum up to 7.01 megabecquerels. So the sample size is 10, we have a total of 77.01, so the mean is 77.01 divided by 10, or 7.701 megabecquerels. To calculate the standard deviation, we have to work out the deviation from the mean of each of those readings. So since the mean was 7.70 megabecquerels, we find that our 7.66 is 0.04 below the mean, 7.67 is 0.03 below the mean, and so on. If we add up all those deviations, it comes to a total deviation of 0.01. Now you may be disappointed that that doesn't come to 0, because I said that in principle the sum of all the deviations should be 0. This is close to 0, but not exactly 0. But if we divide it by 10 to get the average deviation, then it would be close enough to 0 just to account for the rounding errors. In this case the rounding errors were because I took the mean to be 7.70 instead of 7.701. So we don't need to worry about this small sum there. It's close enough to 0 not to matter. The next step is to square all those deviations. 0.04 squared is 0.0016, 0.03 squared is 0.009, and so on. And we don't need to worry about the negative signs on the deviations, because when we square a negative we get a positive anyway. If we add up all those squared deviations, we got a total squared deviation of 0.0221. So the variance, which is defined as the average squared deviation, is 0.0221 divided by 10, or 0.0022. The standard deviation is just the square root of the variance. The square root of 0.0022 is 0.047 megabecquerels. That is the standard deviation of our sample of 10 measurements. First of all, we were asked for the precision of the calibrator. Well, that's quantified by the repeatability over a large number of readings. That would be the population standard deviation if we were able to take a very large number of readings. All we've got is a small sample of 10 readings, so we have to estimate the population standard deviation from our sample data by applying the Bessel correction. Now we've already seen that the sample standard deviation was 0.047 megabecquerels, so our best estimate of the population standard deviation is that multiplied by the Bessel correction of root n over n minus 1, or root 10 over 9, and that comes to 0.050 megabecquerels. Now if you'd used Excel to calculate the sample standard deviation using the function stdevp, you would have got 0.047. If you use the function stdev, you get the answer 0.050. That's just another illustration of the fact that the function with the p at the end calculates the standard sample deviation if it's given sample data, despite the fact that there's a p at the end, and the one without the p at the end gives the best estimate of the population standard deviation if you give it the sample data. So stdev without the p already includes the Bessel correction. So it doesn't really matter which method you use to calculate the estimate of the population standard deviation. The instrument precision is therefore 0.05 megabecquerels based on our estimate of the population standard deviation. The mean was 7.701, so the percentage precision is 0.050 divided by 7.701 and multiply by 100 to make it a percent, which comes out to be 0.65%. So that is the answer for the percentage precision of the instrument, 0.65%. The second question was to look at the source activity. Well, the best estimate of the source activity will be determined from the mean of a large number of readings, the population mean, but our sample mean should give an unbiased estimate of the population mean, so our estimated source of activity is just our sample mean of 7.701. The precision, because we've taken several measurements, can be determined from the standard error of the mean, which is thus the sample standard deviation divided by root n minus 1, or 0.047 over root 9, which is 0.016 megabecquerels. If you remember, the alternative way of calculating the standard error of the mean is to use the population standard deviation divided by root n, which is 0.050 divided by root 10, which is also 0.016. So either of those methods will calculate the standard error of the mean. So the best estimate of the source activity we quote as 7.70, the mean activity, plus or minus 0.02, the standard error of the mean. Notice there's no point in quoting too many significant figures in the standard error of the mean, and if we round that to 0.02, then we also round the mean activity, 7.7, to just 2 decimal places. There's no point in quoting the third decimal place, which is better than the precision of the measurement. We are now asked about the confidence interval. Well, our best estimate of activity we've just said is 7.70 plus or minus 0.02, and what we want to do is determine the likely range of activities that could give a result like that. We've got a small sample, 10 measurements, generally anything less than 30 we consider to be a small sample, so we use the t-distribution rather than the normal distribution. For that we need to know the number of degrees of freedom, and the degrees of freedom is the number of measurements n minus 1, which is 9 degrees of freedom in this case. So what we want is the 95% confidence interval. So we need to know how big a change we would expect before the probability falls below 5%, corresponding to our 95% confidence interval. 5% is a probability of 0.05, so we're basically asking how far out into the tails of the distribution do we need to go before there is only 5% probability of getting it. We look that up in a table of the t-distribution. That's tabulated like this. The probability p goes across the top of the columns from 0.9 to 0.001. We want a probability of 5% or 0.05, which is this column. The different rows correspond to different numbers of degrees of freedom. We want 9 degrees of freedom, so we want this row. So the number at the intersection of 9 degrees of freedom and p is 0.05 is 2.262. That tells us how many times the standard deviation we need to go into the tails before we end up with a 5% probability. So getting back to our calculation of confidence intervals, we found the t-value of 2.26. So the lower confidence limit will be 2.26 times the standard error of the mean below the mean. In other words, it's 7.70, the mean, minus 2.26, the t-value, multiplied by 0.016, which is the standard error of the mean, and that comes to 7.66. Likewise, the upper confidence interval is the mean plus that, which comes to 7.74. So we can say that our 95% confidence interval is from 7.66 to 7.74. If we're having to place bets, we could be 95% certain that the true answer is somewhere in that range between 7.66 and 7.74. There's only a 5% chance that it's less than 7.66 or more than 7.74. Notice if we'd been using the normal distribution for a large sample, then for 95% confidence limits we take 2 standard deviations. Here we've got 2.26 standard deviations from the t-distribution, which confirms what I said earlier, that the t-distribution is just somewhat wider than the normal distribution, so we have 2.26 instead of 2. The precision of our measurement we can determine because we know the best estimate is 7.70 plus or minus 0.02, and the precision is indicated by the standard error of the mean. And as a percentage, it's the standard error of the mean divided by the mean multiplied by 100 to make it a percent. So it's 0.016 divided by 7.7 multiplied by 100, which is 0.2%. So 0.2% is the percentage precision of the measurement. That's pretty good, really, and it's even better than the precision of the instrument, which was 0.65%. So that seems rather surprising, that the measurement is more precise than the instrument. But that's simply because we took an average of 10 readings, and that's what happened. The standard error of the mean is going to be better than the standard deviation of the measurements that contributed to it. That's how we improve our precision, by averaging several measurements. We were also asked for the accuracy of the calibrator, given that our measurement was 7.70 plus or minus 0.02, but the true activity is 8.05, we can see that 8.05 is actually quite a way outside our 95% confidence interval, which only goes up to 7.74 megabecquerels. So it means there must be a systematic error in the calibrator, because our confidence interval only accounts for random errors, and this is a systematic error that isn't accounted for by statistics. So the error, the difference between 7.70 and 8.05, is minus 0.35 megabecquerels. As a percent, minus 0.35 over 7.7 multiplied by 100 is minus 4.5%. So we can see that this calibrator is reading 4.5% low compared with the true activity. So for accurate work, if we want to correct for that, we need to increase our readings by 4.5% to allow for that error. Notice this is nothing to do with statistical error. This is a bias, an inaccuracy in the calibrator, which we have to allow for in addition to any random statistical fluctuations. So finally, we were asked about the technetium activity. We have a calibrator reading of 73.2 megabecquerels for a technetium source, but we know that the calibrator reads 4.5% low, so this measurement will be too low. We need to increase it by 4.5%. 4.5% of 73.2 megabecquerels is 73.2 multiplied by 4.5 over 100, which is 3.3 megabecquerels. So we need to add 3.3 onto our reading, which gives 76.5 megabecquerels as the correct activity for this source. But we know that the precision of the instrument is 0.65%. That was its estimated standard deviation. Notice we've only got one measurement here, so we aren't improving things by using the standard error of the mean. We have to rely on just the instrument precision that we determined previously. So 0.65% of 76.5 megabecquerels is 76.5 times 0.65 over 100, which is 0.5 megabecquerels. That's assumed to be the standard deviation of this result. So the best estimate of the technetium activity would be 76.5 megabecquerels, our corrected activity, plus or minus 0.5 megabecquerels, the standard deviation estimated from the instrument precision. So if we want to quote our 95% confidence limits, we can go 2 standard deviations either side of the mean. Notice we're going 2 standard deviations using a normal distribution now. We don't have a sample of measurements, so we're not using the t-distribution, we're assuming the normal distribution. So 2 standard deviations would be 1 megabecquerel, so 1 megabecquerel below the mean is 75.5, 1 above is 77.5. So we're 95% confident that the true activity of this technetium source is between 75.5 and 77.5 megabecquerels. So that's the end of part 5 of this lecture, and I hope it's illustrated how we can apply some of the statistical techniques that we've learnt about sampling to real practical applications in an isotope calibrator.